Hi, my lovely 13 diplomas, and welcome to topic 16. These are the two sections of topic 16. So we've got rate expression and reaction mechanism, and we've got activation energy. I think the way that I'm going to do this is 16.1 kind of all together in a series of videos, and I think it's easier to learn as a whole and then go back and spend at least a lesson practicing the skills. So the essential idea is here. I'm not going to read it all out to you. I just want to get cracking, but you can pause and have a read if you wish. Here are your understandings that you need to be able to do. I kind of feel this is pointless almost until you've learnt the stuff, and then I think it's easier to go back and tick them off at the end. And here are some application and skills. Obviously, we can't do any rate experiments because we're not at school, but we can when we get back. Okay, so before we get started, here's just some math stuff that might be useful for this. So these are if you've got exponent calculations. So if you've got timesing two things with exponents, then they add, and dividing they subtract. Okay, so let's just get on with the first part of this. I have to say, I reckon this is a really cool topic, and we don't do this in NCA, and so I love that we're doing this together. So what are we going to look at here? So this is an interesting reaction. You don't need to know this reaction for your exam, by the way. This is just an example that works really well. So what this is a buckyball, which you'll remember the buckyball there with some oxygens. So it's how an oxidized buckyball gets decomposed over time. And they can track the changes of this with light absorbance, okay? So they can shine some light through, measure the absorbance, and the concentration of the oxidized buckyball goes down, showing that it's degrading. So because it's converting to this, okay? So we can measure the absorbance, and we know from doing calorimetry in our topic 6 previously that absorbance directly relates to concentration, which is really good. So here's some data that I've just snipped from the textbook. So at certain time intervals, every 6 minutes, they've done the absorbance of the buckyball. Okay, so nice and easy. And it's been graphed, just like you would do, absorbance over time. And you can see it's a beautiful curve. As we know, rate graphs from that revision video you've previously looked at in topic 6, that rate graphs are curves. And just to recap why they're curves, because rate changes are never constant, and the reason why is rate is always highest at the beginning when you've got lots of reactant particles, and then that decreases as you get less reactant particles. Now, how do we define rate? In this specific example, it's actually that the concentration of a reactant changing over time, okay? And it's a negative concentration because we're doing a reactant concentration decreasing. So that's really important. So even though the rate here is negative, that's just referring to the fact that it's a negative concentration. So how do we work out rate? Well, you'll remember to do rate, you have to do a tangent to the curve. Oh, that wasn't a very good tangent to the curve. You have to use a ruler normally. So you draw a straight line to the curve, that's a tangent, and do rise over run. Now, that means that every time you do a tangent, you will get a different rate. And the reason why we can do rate is because we know that absorbance actually directly corresponds to concentration, and the definition of rate is concentration over time. So if absorbance is the same as concentration, then you can do absorbance over time, and it'll give you concentration over time. Okay, so here's a graph of exactly that. So this graph has been created by taking the tangent multiple times. Okay, now that is a lengthy process, but it's totally reasonable. I've had students in the past for their IAs do loads and loads of tangents, and that's how they chose to do it. But the other way that you actually could do it is just by looking at your raw data table, and you can just do the change in absorbance over time. So if we just go back to a results table, so you could do the change in this absorbance over the change in time, and that would give you the rate between those 2 points. And then you could do that each time, if that makes sense, and you could get multiple rate points. So that's the alternative way of doing it, I think potentially a lot easier. Back to here. Cool. So then now this is a rate time graph, and this is so important. So we can see here that the concentration is changing over time, okay, and it's showing that the rate is decreasing over time. So rate's decreasing because the concentration is decreasing. Yeah, and so that's what this graph is showing, nice and easy. So just to recap here, we had an absorbance time graph, okay. Absorbance is the same as concentration, and we can therefore take tangents of this curve, and then we can do and that converts them to rates, or we could just use it from our raw data and we can graph rate over time instead. Okay, and we can see here that all of these are related, so concentration, absorption and rate are all related here. So this is a different sort of a graph. So now we're graphing the rate versus the absorbance. Okay, or instead of doing absorbance, this could be concentration. Okay, now what they're actually saying here is because the rate of the reaction is taking this straight line or making this straight line, it's actually directly proportional to the concentration. And so because we've got a straight line, we know that it doesn't matter where we take the gradient of this line, it's going to be the same. So when the concentration is high, which is down here, the rate will be high. And when the concentration is low, the rate will be low. So we can see here that actually rate is proportional to the concentration. Okay, so we can write that as an expression. So rate of this reaction equals K times the concentration of the oxidized buckyball. Now this K is simply a rate constant for a particular reaction at a given temperature. It's like doing your equilibrium constants, your Ks, okay? So that's the same there. So it's the rate constant. Now we're going to be learning a lot about this stuff, and this is just an introductory section. So if you're kind of like, oh, I'm getting a little bit confused, hopefully things will make sense as we keep going through. Now this reaction is a first order rate reaction, okay? This is the first time you're hearing something like that, and it won't make sense as to why. I'm telling you that, but what it means is that the concentration of the reactant is raised by the power of 1. In other words, you get this nice straight line, okay, where rate is proportional to absorbance. So just pause on this for a second and you can come back at the end and hopefully this makes a bit more sense. We're just going to keep going for now. So rate and rate orders are determined by experiments only. This is probably something that students get confused about and do the wrong thing constantly. Okay, so in order to work out rate of a reaction, it always has to be done through experiments. You can't do it just through a balanced equation. Okay, so if we look here, we can have different rate expressions. Okay, so this is a rate expression where we're using concentrations of A and B. Okay, so here, if whatever it's to the power of, that's the rate order. And right now you don't know how to calculate the rate order. That's what we're going to achieve by the end of these videos. But what we can say is that we can add these two, whatever these numbers were, and they would give you the overall order of a reaction. And we're going to be doing orders 1, 2, and 3 this year. So if this is the rate expression, and this was a rate order 2, and this is a rate order 1, which you don't know how to do yet, I'll teach you. We add those together, and the overall rate order of the reaction would be 3. So this is the order of the reaction with respect to that concentration, and this is the order of reaction with respect to the B concentration. So each substance in your reaction has its own particular rate order of how that is affected in the reaction, and so they will be different. So let's keep going. Okay, let's keep going. So here's an equation. Okay, now we know the numbers here mean is a ratio, number of moles. So 2H2 plus 2NO goes to 2H2O plus N2. Please note, these numbers mean nothing to do with the rate. A lot of people get confused here, and people think, oh, because there's a 2 here on this, it's going to be rate order 2. No, no, no. The only way we can work out rate is by doing an experiment. Okay, now right now we're kind of working backwards at this point in time. I'm giving you a few bits of information and then we'll work back to how. So if I tell you that this is the rate expression, so rate equals the rate constant, and that it's NO to the power of 2 times H2, that means that the concentration of N2 is rate order 2, and the concentration of H2 is rate order 1. So that means that the overall order of the reaction is 2 plus 1 makes 3. Okay, so the critical thing to note is that the coefficients on an equation do not tell you anything about the rate order of those particular reactants. The only way that we can get this information is from an experiment. I haven't shown you how yet. So the first thing that you're just learning is this is what a rate expression looks like, where we write rate equals the rate constant times the order of the individual substances. And this is going to make sense as we go through. And the second thing that you need to understand is the overall order of the reaction is adding the individual orders of the reactants. So what would determine a rate of reaction? The mechanisms. This will be the last lesson I do for this section, so we just can pause on that. Okay, so let's just make sure we've understood this first part, which is that the individual orders add to give the order of the reaction. So if H2 is first order and I2 is first order, 1 plus 1 makes 2, so it'll be second order overall. So if H2O2 is first order, okay, and if there's nothing else here, then that means the overall is first order. Okay, first order and first order equals overall, second order, first order, and nothing means first order overall. So hopefully that makes sense. Let me know if you've got a question. Here, what this task is writing the rate order equations for the following. So I'd love you to pause and try and write a rate order expression. It'll be good to kind of watch one to make sure you've got it. So rate equals the rate constant, so K. Then we do square brackets for because that stands for concentration. So if I put H2's first order, so I don't need to write anything, times what's next is I2, and that's also first order, so I don't need to write anything else. Okay, so could you please pause your video now, try and do the rest, and I'm going to go through and do them now. So number 2 is going to be rate equals K H2O2. Don't need to write anything else. For this one here, rate equals S2O H2 minus I minus, okay, and then this last one, rate equals K N2O5. Cool, I hope that all makes sense. So I'm going to pause here, team, and we will come back and finish the rest in the second video.